warm welcome to our studio guests today and to fellow travelers out in cyberspace, thanks to that non-stop stream of zeros and ones. My name is Peter Gobetz, co-founder of the Zero Project and moderator of the International Conference-/Workshop on Zero. The Zero Project is a three-stage affair. There's a book project, there's an associated online event, and then there's the in-depth research program to follow. But today, session number 14, we welcome two more contributors to the Monograph on Zero book project, Professor Jeffrey Oakes, University of Indianapolis in Indiana, USA, and Jonathan J. Crabtree, historian of elementary mathematics in Melbourne, Australia. I should mention here that Jonathan was the one who early on referred us to Jeff. And at the time, Jonathan and I were both keying on zero from different angles. Both men play a pivotal role in the Zero Project by documenting evidence of the fact that the numeral zero that arrived from India in the Islamic world in the late 8th century was understood only as a placeholder. This astounding fact that has now come to light during the Zero Project was overlooked by countless generations of historians of mathematics, it seems. It raises serious questions as to whether the invention of zero was a disruptive moment in history, or rather a slow evolutionary process only interpreted in retrospect as a sharp distinction. We welcome as panelists today Dr. Jim Ritter, Emeritus Professor, or rather a special status at the Sorbonne University of Paris. He is a historian of science and theoretical physicist. Professor Friedhelm Hoffmann, Ludwig Maximilian University of Munich in Germany, and Professor Mayank Vahia, astronomer, formerly the Tata Institute of Fundamental Research in Mumbai, India. Session 14, therefore, sees represented four of the world's major civilizations that each in their own way played a role in the zero story: Mesopotamia, Egypt, India, and the Islamic world. So without further ado, and our focus will be throughout on the distinction, if any, between the placeholder and the number zero, may we invite you, Jeff, to briefly introduce yourself and tell us what you have found out on this issue.
Yeah, sure. Is this going to be my entire talk right now? So, okay, there goes. One of the many paths that the Indian numerals took from their origin in India around the 1st century AD, roughly speaking, was passed to the west through the Islamic world and then onto the Latin West in the medieval times to the numbers that we use today. So understanding how zero and the other digits were conceived in medieval Islamic civilization is kind of critical to understanding the transmission from one to the other. So we're really fortunate that so many books survive in medieval Arabic on arithmetic, and that many of these are textbooks intended to explain the idea to beginners. So I've had a lot of fun looking over these books. And as far as I know, no one has actually done any serious investigation into that concept of zero in Arabic before. At least I couldn't find any secondary sources on it. So, so this certainly warrants an investigation. And when you read over these books on Arabic arithmetic, particularly the ones on Indian calculation, you'll find that the zero is operated on just as the other digits are in these calculations. But at the same time, an author will say that the zero is a sign for an empty place where no number resides, which may seem like a kind of a contradiction. So it's certainly worth looking into to see what's going on here. So I'm going to break this talk up into 4 parts. First, I'm going to give an overview of Arabic arithmetic, of which Indian arithmetic was just one part. Then I'm going to address how medieval authors conceived of numbers. And then I'm going to pay attention to how nothing was conceived and dealt with in arithmetical problem solving. It is literally nothing. And then finally, I'm going to address the zero found in the books on Indian calculation. So that's how it's going to go. So in medieval Arabic, there were 3 main ways of performing calculations. One of them was finger reckoning. In finger reckoning, calculations were done mentally, and intermediate results were stored by positioning the fingers in particular ways. So this was not a written method. This was a method that was commonly used among merchants and government secretaries and others. Probably the most common method of calculating in the medieval Islamic world. And the second is sexagesimal arithmetic, which would be the base 60 system of the astronomers that Islamic astronomers acquired from both Greece and Mesopotamian sources. So, and the third one, of course, was Indian calculations with 9 digits and the 0, which they acquired from India probably in the late 8th century. So, in the second of these, the third, in the sexagesimal and in Indian calculation, the calculations were performed on some ephemeral surface like a dustboard where it's easy to erase and rewrite digits. You're going to see that in some of the calculations I'll show you in a minute. And if one wanted to compose a book on calculation, one actually translated all of these calculations rhetorically so that everything was written in words, including the numbers themselves, they're written in words. And the figures only occur in books as illustrations to show what you should write on the dustboard. So could you show the first slide? Kevin. Oh, here we go. Yeah, so this is just a sample page to show you what these texts look like. On the left, we have a page from a book by Alhasar written around the year 1100. And you can see that he's written the figures for the Indian numerals in red, and the rest of the text is in black. And that's everything written in words. In fact, what you almost always find is that the numbers that are expressed in the red ink are written out in words ahead of time, and then they'll say, and its figure is, and then show the diagram. So now numbers in these texts consist of any positive amount that they could calculate from the unit by any of the arithmetical operations: addition, subtraction, multiplication, division, and root extraction, including square root, cube root, fourth root, fifth root, etc. And show the next slide now. So just to give you one example, here's a sample in notation of a rather complicated irrational number, positive irrational number, expressed in notation in a book from the 15th century. And this, I'm not going to read it to you, but this amount is written rhetorically right before it's shown in the picture. So this is the illustration in the sort of the upper right-hand part of the page you see on the right-hand side, but it's all written in words first, and then he'll say, and its figure is, and then show the notation. So that sign you see above the numerals is the first letter of the word for root, jither, and that indicates square root of those texts. So this is just to give you an idea as to what these texts look like. And here we are. Oh yeah, so not only did they have these 3 ways of calculating, plus a few others that are not so important, but they also appropriated Greek number theory from the texts of Aristotle and Euclid. So in this system, numbers are noetic unit. Numbers are aggregations of noetic units. So off somewhere, if you're a Platonist, these exist in the realm of ideal forms. If you're an Aristotelian philosopher, then you regard the objects themselves as being potential units. And but everything was done in an abstract sense. And so there was a problem here between the Greek numbers and the practical Arabic numbers, and that the Greek numbers are assumed to be, how should I say that? Let me repeat that. That the unit in the Greek mathematics is assumed to be indivisible. So what kind of unit is it if you can divide it into pieces, I suppose? So they only regarded numbers as being positive integers. Those are the only possible numbers for Euclid and Archimedes and other ancient Greek authors. Although practitioners worked with fractions at the same time, but we don't find those in the texts. So there was a little bit of a problem here because there are a lot of ideas in the Greek arithmetic that were appropriated in the practical arithmetic, and they kind of mix the two together without really worrying too much about the fact that their number concepts were quite different. Now, both of those number concepts are radically different from our own, in the sense that numbers for them always had to be numbers of something. Numbers for us are very different. If I've asked my students this before, I say, what is number 3? What kind of object is it? And they usually hesitate because they're not quite sure what to say. These are students who have not had my real analysis class yet. So they will, so some of them will say it's like 3 things, and of course, then we have to back up. So just to Okay, so if you're a mathematically trained person, a number is going to be any element of a set which, together with operations we call addition and multiplication, satisfy the ordered field axioms. Or if you're someone who doesn't have this mathematical training, a number is going to be some point on some imagined number line that you were told about when you were in school. So we have this number line here, and the zeros in the middle, and 1 is off to the right, and and the negative 1's off to the left, and so on. And if you're a child, most likely you think of numbers as being things, counting numbers. So let children count 1, 2, 3, 4, 5, and so on, usually without any regard to anything they're counting. And what all of these concepts of number have in common is that numbers are objects in themselves. They don't necessarily modify or count or measure any particular unit. This was not true for the ancient Greek numbers or for medieval practical numbers. Numbers in pre-modern times were always numbers of something. They were more like adjectives than nouns. The number 5 didn't exist by itself. It had to be 5 something. It had to be, so you could have 5 horses, 5 myth cows of grain, where a myth cow is a unit of weight. It could be 5 hours, 5 degrees, 5 sevenths, 5 thousandths, 5 intelligible units, but it has to be 5 of something. It's kind of like the numbers can't exist, kind of like the color red can't exist unless it's in an object that is red. The numbers can't exist unless they count or measure something. In fact, the material, the matter of number was the objects that they were counting. So the number of 5 horses is the horses, just seen from the perspective of quantity. And so numbers consist of 2 aspects. It's the quantity and the species. The quantity is how many or how much, and the species is the kind of unit. So this is something that has to be kept in mind when we read these texts, which is usually neglected by people who study pre-modern arithmetic. So, of course, it'd be interesting to know if 0 was a number, and that's a question which I was thinking about when I started this research. And the first thing I did was look to see what definitions we might find in these textbooks. Well, it turns out that medieval Arabic arithmeticians tended not to give any definition of number. They just begin working with them right away, presuming you already know what a number is. Some books will give a definition, but they just give the Euclidean definition and then disregard the fact that that definition implies that the unit is indivisible, and they go ahead and work with fractions and irrationals anyways. The definition is kind of like just a theoretical dressing for the beginning of the book to make it look more respectable, I suppose. So we don't have definitions to provide. So what we can, if we read the books, we can find, as you saw in the last slide, examples of fractional amounts and irrational amounts. And they're always positive. There are no negative numbers that stand by themselves in Arabic mathematics. There are numbers that are subtracted from other numbers, and there are rules for operating on numbers that are subtracted, but that's not the same as a negative number. So now I'm going to turn to arithmetical problem solving in Arabic arithmetic. So many of these books have a collection of a couple of dozen, maybe 3 dozen, maybe more, worked out problems that one is supposed to hone one's skill with. And these occur mainly in the texts on finger reckoning, so they're not associated with the Indian numerals at all. And so a lot of these problems will ask for, say, how long it takes for 2 rivers to fill a reservoir, how much money each man has who wants to buy a horse, the weights of gold and silver in a piece of jewelry or something like that. Or more frequently, they'll be asked in terms of some abstract units, because the practical mathematicians have abstract units as well, where they're not, in some sense, they're not specifying units, but it's always presumed that there is some kind of unit there. So some of these problems will actually be solved. Some of these problems will actually be posed in which a person or some amount becomes nothing. So could you show the next slide? So this is a page from the algebra book of Abu Kamil, who worked in the late 9th century. In this book, of course, he's not teaching how to calculate with numbers, so all numbers are written in words. There's no notation anywhere in the entire book. It's all text. So, in fact, on this page, maybe about 3/5 of the way down the page begins a problem, and I'm going to read my translation of the enunciation, which goes like this. A man has some money. He does business with it and profits the same amount, and he gives 10 dirhams in alms. Then he does business with it and profits the same as what remained, and he gives 10 dirhams in alms. Then he does business a 3rd time with the remainder and profits the same, gives 10 dirhams in alms, after which he is left with nothing. So this is one of the many problems I found in Arabic books in which something turns out being nothing in the end. Literally nothing. La shay means no thing. That's how they expressed it. So Abu Kamal solves this problem by algebra. There were several different problem-solving techniques that people used. Algebra was just one of them. So show the next slide, and we can look at the solution here to see exactly how he handles it. So on the left, I kind of put modern notation. On the right, I have the translation. So in step A, he says, its rule is you make his money a thing. The word shay, thing, was a name given to the first degree unknown. We'll call it an X. He does business with it and profits the same, which is a thing, so it becomes two things. So he has 2x. He gives 10 dirhams in alms, leaving 2 things less 10 dirhams. So now he has 2x minus 10. That's his amount. And then it continues with the calculations down until the end. And then, so he profits the same in the end, getting 8 things less 60 dirhams, or a dirham is a unit of currency. And now, at this point, he would have to give 10 dirhams away and then be left with nothing. But rather than state an equation with 0 in it, Abu Kamal just equates this 8 things less 60 dirhams with the 10 dirhams that he gave away, explaining it. So he hesitates here, doesn't quite want to make an equation that has something where one side is actually equal to nothing. He doesn't want to do that. He hesitates on this. So that's kind of interesting in itself. I'm going to bring this up in a second also. So most problems of this type are stated in more abstract terms, such as a problem in Al-Khwarizmi's book, which is from around the year 1300. He states this problem. If someone said quantity, you add to it its fifth and 5 dirhams, and you subtract from the outcome its third and 5 dirhams, it leaves nothing. So there's another problem, but this one's stated more abstractly. And again, you follow the solution. And Al-Khwarizmi is one of the people who actually will set an equation equal to nothing. So I don't know if he does it in this problem or another one, I can't remember. But he solves this particular problem 3 different ways. He solves it by algebra, and then he solves it by working backwards, then he solves it by double false position, which I won't have time to explain. So I found 36 problems whose enunciations end with nothing among the worked out problems in 21 books by 19 different authors, ranging in time from the 9th century to the 17th century. So this is a fairly common occurrence that we find here. In 16 of those problems, a solution by algebra is given, 16 of them by 11 authors. In 4 of those, an equation with nothing on one side occurs. It didn't occur in Abu Kamal. He didn't do it. He was hesitating there. But it does happen in Ibn al-Banna. And so he said, in fact, he solves the same problem Abu Kamal just did, except his businessman just gives 1 dirham an ounce instead of 10. He was a little stingy than the other guy. So in fact, he states the equation like this. Then gaining its same and giving a dirham in alms leaves him with 8 things less 7 dirhams, and this equals nothing. So he says that this particular, he states an equation here that it equals nothing. Now, what's really nice about this is that later on in the year 1370, another person, Ibn al-Qunfud, wrote a commentary on a book of Ibn al-Banna, and he copied this problem into his book. And he gives the algebraic notational version of this solution. And show the next slide. We're going to see what that looks like here. So he wrote a book called Removing the Veil from the Faces of Arithmetical Operations, which is a commentary on a different work of Ibn al-Banna. I don't know if you can see it or not, but there is red ink in there, which indicates notation. And on the next slide, I blew it up so we can see what it looks like. So show the next slide. So there it is on the left-hand side. And this is what we would call 8x minus 7 equals 0. So you can see the 8 on the far right. Remember, Arabic is read right to left. The 3 dots above the 8 are the 3 dots from the letter shin, which is the first letter in shay for thing. So that kind of indicates that that's what our x would be. To the left of that are 2 lines, one curvy and one angled. That's a sort of a stylized illa, which means less. Then to the left of that is 7, which looks like a 7. And then this big loopy thing in red, that's the last letter in the word for equals. And so I just wrote equals. And then you see that little 0 there to the left of that in red ink. So this is the only instance I've seen in any Arabic text in which 0 stands by itself to indicate an amount. So, I mean, at this point, someone might say, oh, it's obviously a number, but we shouldn't really jump to conclusions here with respect to that. And I'm going to talk about this. I'm going to bring this equation up in a little bit. So anyway, I'm going to set it aside right now. We're just going to keep that in mind, because right now I have to look into how 0 is treated in Indian calculation. So we've done all of that just to get to the text where we actually solve problems using the Indian numerals. So I looked at 34 different medieval Arabic books by 31 different authors, ranging in date from the 9th to the 18th century, written in place from Morocco to Central Asia, and some of them are by prominent mathematicians like As-Samawal, Nasir ad-Din at-Tusi, and Al-Kashi, if you happen to know these people. Others were written by practitioners. One is an anonymous guide for government secretaries. So they're written by people from all walks of life who are interested in calculation. And one of these books is by Ibn al-Bana, who I've already mentioned before. In this particular book, it's called the Condensed Book on Calculation, and it is so condensed, he doesn't show the numerals. Doesn't give one example in the entire book. He just explains the rules. But setting aside his book, the other 33 books all introduce the digits 1 through 9 independently, and then show the 0 only later and explain what it means. So, which itself indicates that the 0 is somehow to be set aside. So I'll show the next slide. So these are the 2 pages from a book by Al-Nisaburi from the 10th century. And so it begins on the right-hand page. So this is the chapter where he begins explaining how the digits go. And he shows them in red. Of course, it's a figure. It has to be shown in red. That's not part of the running text. The digits 1 through 9. And on the next page, he shows variations from other places or other authors. So a lot of these books give variations on the shapes of the numerals. They didn't have one particular form at any one place in time. And I show them enlarged on the far left there, starting from the right, 1 through 9. The 1 looks like a 1, the 9 looks like 9 for us, but the ones in the middle look a little bit different. These are the Eastern forms from the medieval period. So anyway, show the next slide after this. Here's a part of a page showing the Western forms. That you can break down the shapes of these numerals between East and West, although there were a lot of variations in between them, and even among individual authors writing around the same time. But right around where I have, this is from Ibn al-Kunfus' book again, the one where we just saw the notation. But you can see the Western forms about in the middle of the page. And those look very much like the modern Western forms now, except for the 4 and the 5, which are actually still pretty close. And he shows variations also, some rather crazy variations, which I won't have time to discuss at this point. So this is how the numbers are introduced, so the digits anyway, 1 through 9. 0 is introduced later. Usually it's introduced a page or 2 later in the process of explaining how the place value system works. So 0 does not pop up immediately. So I'm going to read you now some of the ways that 0 is explained after these digits are described. So and the first one comes from Al-Khwarizmi. Muhammad ibn Musa al-Khwarizmi worked in the early 9th century in Baghdad. He wrote the oldest known book on calculating with Indian numerals in Arabic. Unfortunately, his book is lost, but we have a medieval redaction, Latin translation. That's all we have of this book. And in that book, which comes from, I think it was written in the 12th century, he says, well, in the Latin translation, it says, to explain how to write the number 10, given the 1, he writes, so they put one space in front of it and put in it a little circle like the letter O, so that by means of this they might know that the place of the units was empty and that no number was in it beyond the little circle, in which we have said occupied it. So he's saying that you put this little circle, this little O, where there is no number. And now we have Al-Uqaydizi. Al-Uqaydizi worked in the middle of the 10th century, and he wrote the oldest extant Arabic book on calculating with Indian numerals. And he says, at one point, then he is informed that some of these places may be empty, with none of the 9 figures falling in it. If this is the case, a circle is set in the empty place. This is what the people of this craft call a 0. And now I'll read you what Al-Nisaburi wrote. Al-Nisaburi was the first one I showed you a second ago. If there is no number in it, place there is 0, which is a small circle. As-Samawal, who was a famous algebraist, wrote, you write in empty rank sorry, actually, show the next slide, because I think I showed this picture. Yeah, here it is right here. This is the page from Bassamilla's arithmetic book. And he wrote there, what you write in an empty rank to take the place of its emptiness is called a zero, and it is this. And then he shows it. Show the next slide now, because this is going to be a blow-up version of that. So he introduces the 9 figures, which are written rather small all the way across the page above the 2 blocks of digits. So the 2 blocks there are showing variations. And immediately, he's unusual, and immediately after showing the 9, he explains that the zeros is a sign for, expresses its emptiness. So that's Bassamilla. I don't know how many more of these I should read. Well, Alhasar, working in the late 12th century, writes, one needs to put something in the unit's rank to establish the rank, so that one will know that the unit's rank has nothing in it. Thus, the arithmeticians put a 0 in it in the form of a small circle. Or Nasir ad-Din says, he's the famous astronomer and theologian from the Moraga Observatory. He wrote, and you put a 0 in the form of a small circle in every rank devoid of a number. And Al-Kashi, famous mathematician who worked in Samarkand, famous astronomer and polymath effectively, he wrote, a 0 in the form of a small circle must be placed in every rank where there is no number to avoid a gap in the ranks. And I guess I'll read one more here. From an anonymous text from the 16th century, a 0 in the form of a small circle must be placed in every rank where there is no number. Oh, sorry, that was Al-Kashi. I'm reading the wrong one. Oh, and if you want a 10, put it like this. Then he shows a figure for 10. Since the unit's rank has no number in it, you put a 0 in it to keep the place for you, and it will be clear to you that it is not a number. So the texts I read are unanimous in saying that the 0 is to be placed in an empty place where there is no number. So, and that's certainly kind of odd if you think about the fact that they're operating on it. So I'm going to pass to that now. But first of all, I want to point out that today we actually do something like this, and we write tables of numbers. If there's no number, if there's no data in a particular place, sometimes we put a sign there to indicate no data. So show the next slide. So here are 2 examples I pulled off the internet. One's from an article on pollution in wastewater or something like that. You can see in the first one, they put dashes where there's no data available. In the other table, they put ND where there's no data available. In other tables I found have an asterisk or a slash or a double asterisk or some other sign. So the idea of putting a sign in an empty place is not alien to us because we do it here quite frequently. And because we normally think of a 0 as being a number, when we would look at the number 5,042, for instance, we just automatically think of that 0 as being a number. What I'm going to do in the next few examples is put like a bullet point, put it like a filled-in small circle in place of the 0, just to get ourselves out of the habit of thinking of it as a number. So I'm going to give you some examples now operating on 0. So I'm going to talk about addition first. Addition, most books don't give any definition of addition. Even Euclid doesn't give an definition of addition, because all addition was the gathering together of 2 amounts. If you have 3 horses here and 5 horses there, you just put them together and then you have their sum, 8 horses. So this is not a binary operation on some abstract set. It's just literally gathering together 2 amounts. So maybe if it's length, you're putting 2 amounts, one to the end of the other. Or if you're talking about Euclid's abstract units, you're just thinking of those 3 units and those 5 units being gathered together. And this is how addition was conceived in these practical books also. So where are we now? Oh yes, show the next slide. So this is a bottom of the Tehran manuscript of a book by one AlHawari, who wrote in 1305 a commentary on a book by Ibn al-Banna. And I've translated down here what he's written at the bottom of the page. Suppose we want to add 4,043 to 2,685. We write the add on a line in the again below it, on another line parallel to it, as mentioned, as in this figure. So you can see he writes it out in words first, and then he shows you the figure in red ink, which is quite nice. So in fact, you can see that his 0, oh, by the way, they read numbers just like we do. We read Arabic numerals backwards, Arabic numbers backwards, because we medieval copyists understood them to be illustrations or figures, so they did not reverse the direction. So when an Arabic person is reading the 4043 right to left, they encounter the 3 of the units first. So the figures will look just the same. So you can see that the 0 in 4043 in AlHawari's example is much like the 0 I put in here, this little bullet point. So in fact, when you say it, you say 4043. You don't say the hundreds at all. The hundreds aren't there. There are no hundreds to speak of. But then you have 2,685. You have hundreds. There are 6 of them. So he's going to add these 2 together. Now, Ibn al-Yasamin, another author from the 12th century, gave the instruction, then you add each digit of one of the addends to its counterpart in the other. If there is no counterpart, then the answer is the addend, as if it had a counterpart. And that's how AlHawari actually works this thing out. So let me find where I can get here. Yeah. Oh yeah, so AlHawari said here, I bring the slide back up again, the same one, so we can look at the numbers. 4043. So AlHawari writes, we add the 5, which is in the first place of the lower line, to its counterpart in the upper line, which is a 3, giving 8. We put it above them. Now, actually, I recorded this, didn't I? Yeah, play recording number 1. I forgot that I recorded this. So AlHawari gives these instructions for adding 4043 to 2,685. First, you add the units, the 5 in the lower line to the 3 in the upper line, and you put an 8 above them. Next, you add the 8 to the 4, which gives you 12. So you put a 2 above the 4 for the units. And then for the 10 part of the 12, you have to add 1 to the 6 in the lower line, making it a 7. And then he says, nothing in the upper line corresponds to the 7. So the 7, is considered to be the sum of that rank and that of its counterpart, as if it had something. And then, so we put a 7 up here, and then adding 2 to 4 gives us a 6. So 6,728 is the answer. So that's how he does it. He doesn't say we're adding 0 to the 7, although some people did. I'm going to mention that in a second here. Let me just make sure I get to I do everything in order here. Yeah, so once in a while, very rarely, you'll find someone like AlAssad who worked in the 15th century. AlAssad does actually add 0 to numbers and adds numbers to 0. So he has the example of adding 5,023 to 2,502. And then he writes, add the 2 to the 3, giving 5, put it in the units rank. Then add the 0 to the 2, giving 2, which is the answer. Then add the 5 to the 0, giving 5. Put it above the 5. So he actually adds the zeros, and without any explanation as to what they would mean. Now, I have a conjecture as to what it means, and it's based on something I'm going to explain a little bit with multiplication. That if you think of adding, what would you see? He's adding 0 to the 2. If you have a purse with 2 dirhams in it, 2 silver coins, and you add nothing to it, then you still have 2 dirhams. So it would make sense intuitively that if you're adding nothing to an amount, it leaves the amount unchanged. Or if you have an empty purse, nothing in it, and you add 5 dirhams to it, you're going to have a purse with 5 dirhams. So one could conceive of the operations in this way as actually being performed. So I think that's what he's doing here, and I'll have better evidence for that in a second when we talk about multiplication. In fact, I'll do multiplication now. I'm not going to do subtraction because it doesn't really add anything to what I've said before. It's in my paper at any rate. So for multiplication, multiplication is more complicated than addition or subtraction. So Euclid does give a definition of this. In fact, it's the Euclidean definition that we usually find in books on Indian calculation. So Ibn al-Yasamin, who I've already mentioned, gave this definition. Know that multiplying numbers, one of them by the other, is that you duplicate one of the numbers by the quantity of what is in the other number in units. So to multiply 3 by 4, you duplicate the 3 4 times. That's how it works. And almost all books that I looked at on Indian calculation give this definition. There's another definition finger reckoners had, but that's not really relevant here. So there are a lot of different ways people in medieval Islamic countries multiplied numbers, many different techniques. The most common one is by erasing and shifting. And I'm going to have to play one example of that. So play the next video clip, which will explain how this works. So we'll need to see that in order to understand what the authors are saying. So I'm going to explain how multiplication by shifting works. This is a common method of multiplication in medieval Arabic. And this example comes from Al-Uqaydi's 10th century book. So we're going to multiply 34 by 26. And notice that 26 is arranged so that the units place is under the highest place of the 34. So we're going to first multiply the 3 by the 26. And after we're done with that, we're going to shift the 26 over and multiply the 4 by the 26. So that's the shifting part. The bottom number gets shifted. So we begin with the highest places. 3 times 2 is a 6. So we put a 6 here next to the 3. Then we'd multiply 3 by 6 and get 18. So numbers that were here before, like the 3 and the 34, get erased. And I've got to add an 18 in here. So an 8 would go here. And I have to add a 1 to the 6 to put a 7 there. So now, so far, I've got a 78. The 4 that comes from the original number. This is not considered to be part of the answer. So the 26 now has to be shifted 1 space to the right. So I have a 26 here now. Now I multiply the 4 by both of these numbers. 4 times 2 is 8. So I add an 8 to the 78 above, giving me 86 in those places. And then I multiply the 4 by the 6 to get 24. So the 2 gets added to the 6 to give me an 8. And the 4 gets replaced with the 4 from the 24, so it stays the same. So the answer is 884. That's how it works. Yeah, so when we read some of the comments we will make, you have to understand what the shifting means. In fact, I'm going to read what Nasir-ad-Din at-Tusi says about multiplication. He writes, and if there is a 0 in the rank of the multiplicand, we do not need to shift to it, the upper number. We do not need to shift to what, so we shift to what is on its right and calculate the remaining ranks. So if you have a 0 up there in the top number, don't shift under it because there's no point in doing that at all. You're not going to accomplish anything. And if there is a 0 in the rank of the multiplier, there's no need to multiply by. So in fact, most authors will not bother multiplying when there's a 0 present. They won't even mention it. They won't even say, and we skip over the 0. They'll just go right on to the next number. So, but sometimes you have to do the multiplication because you have to put a 0 to keep the place. If the answer to your number has no zeros in it, you're okay. You don't need to bother multiplying by 0. But if there is a 0 in your answer, like if the answer is 205, you have a 0 there, then you're going to need to put a 0 there somewhere in your answer. So play the third and last clip. This is from As-Sardafi's book. So here's how As-Sardafi multiplies 200,002 by 203,003. First, he says, multiply 2 by 2 to get 4. Then multiply the 0 by the 2 to get 0 and put it above the 0. We have to perform this multiplication because if we didn't put anything here, put no sign here at all, the place would not be filled. We have to have an indication that there is nothing in this particular place. 3 times 2 is a 6. We put the 6 here. Also here, we have to multiply the 0 by the 2 and the 0 by the 2 again. And then 3 times 2 is a 6, which puts a 6 right there. So we had to have these zeros here to keep the places. Otherwise, we might think this was just 4, 6, 6. That's why the multiplications were performed. Now, at this point, according to the instructions of Nasir-ad-Din at-Tusi and others, we would have to shift this 203,003 over 1 unit and then multiply by the next digit. But there's only a 0 here. So we don't shift under a 0. We don't shift under any of these zeros. The next thing to do is to shift all the way over underneath the last 2. So we have here a 3, 0, 0, 3, 0, 2. So this is what we have now. And now we perform the last row of multiplications. 2 times 2 is a 4. 4 added to 6 gives us a 10. So we put it there. 2 multiplied by 0. We don't have to perform this multiplication because there's already a 0 here. So there's no need to mention it like he had to over here. 2 times 3 is a 6. We have nothing here. And then finally, 3 times 2 gives us a 6. And this gives us our answer, which is, let's see, 40,601,006,006. And that's the answer. So Al-Uqaydi explained what's going on here. He said he has queries on operations at the ends of his chapters, and one of them is, why is 0 by 0 equal to 0 and 0 by any figure 0? we say that by multiplying 0 by 0, the aim is only to occupy the place. This applies for multiplying a figure by 0. We multiply the figure by 0 only once, the first time, by the first figure in the upper line to occupy the place and tell that this is a place and that it is empty. So what now it becomes a little bit more interesting because we have two people, actually there are four, but two of them are a little bit iffy. We have two people who explain what it means to multiply by a number, not just to keep the place, but actually what it means to multiply. So one of them is Ibn Munim, who are writing around the year 1200, wrote, and know that anything multiplied by 0 is 0, since the 0 is a sign for nothing and nothing is gathered from duplicating it. So he's kind of recalling the duplication method, definition of multiplication, which is you duplicate a number you duplicate an amount by the number of units in the other number. Duplicating 0 just leaves you with 0. Ibn al-Banna expressed it even better in my view. He said, multiplying a number by 0 or 0 by a number is that you zero the number or you duplicate the 0, and neither of them gives a number. So its sign is always a 0. So he's thinking of that duplication definition from the perspective of both amounts, from the amount, from the number being duplicated and from the duplicating number. So, and it does make sense too. If you have no money and you triple your money, you clearly still have no money. You're duplicating nothing. So however many times. So even here it makes intuitive sense to operate on nothing. We're not operating on 0. 0 is the name of the sign to indicate an empty place in the Arabic number system, in the Indian number system. So so when they talk about the operations, sometimes they say 0, sometimes they say nothing, which is what the 0 indicates. So now looking back at Ibn al-Khunfuz's equation, where in modern notation we'd say 8x minus 7 equals 0. The numbers in this notation are Indian numbers, as you saw from the 8 and the 7 in that equation. And if you're writing it in notation, which they did frequently, and something ends in nothing, if you want to have an equation equaling nothing, which you can do because you can take something away from its same and end up with nothing, how are you going to write this nothing in notation? In notation, you have to use Indian numerals, so he put the 0 there, which is really a new use of 0, at least for me. And you might think that perhaps someone who does this often enough might end up developing a more formal view of how this 0 operates. The 0 might actually sort of take on a life of its own just through repeated use in these calculations, but I haven't seen any evidence that took place. That was certainly a possibility. Now, of course, we lack almost all dustboard calculations that were ever performed because they were ephemeral, and we don't have a lot of books people wrote too. So it may have happened a lot of times that people wrote equations with 0 on it. We just don't know. But I don't see any evidence at this point that anybody took any more formal view of the mathematics than what I've just said, than what I've just shown. So it was a sort of a notational way of expressing a rhetorical equation with nothing on one side. That 0 literally means nothing. So I want to finish with one quotation from AlHawari, who I've mentioned before, who wrote his book in 1305. At one point in his chapter on algebra, he does something kind of interesting. He actually operates on nothing, completely outside the context of Indian numerals. But I'm not going to give you the whole context because it would take too long to explain, but just listen to this. He says, and if we continue the solution, we subtract the number from the square, leaving nothing. We take its root, giving nothing. We add nothing to the half, or we subtract it from it, leaving the half. It is the root, and its square is the number, so know it. So he just performed 3 operations involving nothing, literally nothing. And these all make sense if you think of nothing as being just no amount whatsoever, but like nothing being the nothing you're adding to the purse with 5 dirhams. If you think of numbers that way, then that's what you've got. If you think in modern terms, then this nothing must be something because you're operating on it. But today we tend to think in a very different way than they did back then. So today we have an abstract set with a binary operation we call addition on it. And if you can add 2 things together, they must be elements of that set. Therefore, they must be numbers. That's not how these people were thinking. Numbers were positive amounts. And you can see in many of the quotations I gave you, they literally said that the 0 is not a number, explicitly, repeatedly, in every text. So that's and I never saw any evidence, as I mentioned, that the 0 became anything else but a sign for an empty place. That's it.
Thank you, Jeff. Thank you. Thank you. I think it's crystal clear that the numeral 0 seems to be a modern convention, and that us focusing on the invention of 0 puts a different light on it. We should probably not be looking for a moment way back in history when some dramatic event took place and somebody, probably not Eureka if it was not in Greece, but said, now we have a number 0. They just simply used it as their intuition guided, and over time it evolved into something that we now call a 0. It's too early to conclude. I'm not concluding. I'm just sort of summarizing that from the evidence that you have given, that this is becoming clear. This is quite late in history. You're talking about up into the 15th century. So thank you very much for that. We're running a little long. The panelists have to get a shot at this as well, and I think they'll point this out, that arithmetic is not the deciding factor here in this. We have to look for it elsewhere, which we will in due course. But let's take it one step at a time. So thanks, Jeff. I really appreciate it, all the effort you put into this. Jonathan, if we may invite you to briefly introduce yourself and then give us the thrust of your paper.
Thank you very much. My name is Jonathan Crabtree, and I am a naive mathematician. I am an amateur mathematics historian. So I don't work out of a university. For the last 10 years or so, I have just been pursuing my love of research into what I call the lost logic of elementary mathematics. And that lost logic that I've been researching involves the number 0. And it's a long time trauma / love affair that I've had with this, because as I will mention shortly in my presentation, I noticed problems with mathematics because of 0 back in 1968 when I was a 7-year-old boy. So I'm a little different from nearly everybody else involved with the 0 project in that I'm more of a detective. I'm pursuing a cold case, and the cold case for me involves who murdered the definition of 0 as it was originally created in India. And the point of my research is that almost no mathematics teachers in years K to 8 currently even understand how 0 operates and was initially defined. So my research is for the purpose of shaking up the world's understanding of 0 in classrooms today to make mathematics much simpler to teach and learn. So are you wanting me to share my talk now? I can commence if you like.
Can you hear me, Jonathan?
Yes, so I'm wanting to share my slide. Can you see a photograph of children?
No.
No? It says StreamYard.com is sharing your screen. So it should be, there we have it. Okay, fantastic. So this is me in grade 2 in 1968. I'm the child sitting in the front row on the far left-hand side. And you can see on the right-hand side is my grade 2 teacher, Miss Collins, with whom I argued about 0 when I was age 7. So what happened is I I noticed that the English definition of multiplication that my teacher had quoted defined AB as A multiplied by B equals A added to itself B times. And the dictionary definition of multiplication today is to multiply A by positive integral B is to add A to itself B times. Now, my teacher said that 2 multiplied by 3 equals 2 added to itself 3 times. So she asked the grade what that would equal. I put up my hand and answered the correct answer of 8. And then we had a bit of an argument because my teacher said 2 multiplied by 3 was 6. And yet the definition that she gave, 2 multiplied by 3 equals 2 added to itself 3 times, that had been wrong for the previous 398 years. So from 1570, if we passed the English language definition of multiplication literally, 1 multiplied by 1 would equal 1 added to itself 1 time, and that equals 2. So at the age of 7, I noticed that there was a problem, and that was pretty simple, and that was that it should have been explained to the class that there was a 0 involved, and 1 multiplied by 1 equals 1 added to 0 1 times. So the word itself shouldn't have been in the definition of multiplication. The word 0 should have been there, and yet this definition of multiplication is attributed to Euclid from 300 BCE, and so nobody ever changed it because they thought it was Euclid's definition. Now, my research, spanning about 16 different language translations of Euclid's definition of multiplication, revealed it was actually an incorrect translation, and Euclid's definition of multiplication was in effect A multiplied by B equals A put together B times. So that's what Jeff mentioned before as one of the concepts of multiplication. But the Indian approach really involves the use of 0, and that's not in the definition of multiplication today. So the paper that I have written, and I've got you'll be pleased to know, I've got a nice fresh draft available for you, Peter. The title I've given it is Notes on the Origin of the First Definition of 0 Consistent with Basic Physical Laws. So you can see here a balance pan, and we know that when the forces on each pan are equal, then we have equality, we have an equilibrium. The pan on the right pushes down and lifts the pan up on the left, and vice versa. And we have a very simple idea of the concepts of physics in balance in that diagram. So in short, the abstract of what I'm on about is Brahmagupta's definition of 0 as a sum of equal and opposite quantities is the first scientific definition of 0, subsequently consistent with laws of motion and particle physics. So if mathematics is the language the universe was written in, Brahmagupta's Sanskrit text describes a 0 as old as the universe. So we have a lot of philosophy that creeps into our ideas of a linguistic interpretation of a 0, but as far as the universe is concerned, some even theorize that the universe came from nothing, from 0. So, however, having originated in the East, the full power of India's symmetric and scientific 0, and I say scientific because the Indians were astronomers, not philosophers and geometers as people were in ancient Greece. So the full power of India's symmetric and scientific zero failed to migrate west via the medieval Arabic world to Renaissance Europe. And Jeff has brilliantly given us many examples of how zero wasn't really interpreted as a number in the Arabic world. So therefore, I advocate for a hypothesis where only a trivial mathematical concept of zero emerged, representing either nothing on its own or as an arithmetical placeholder used alongside other numbers. And Jeff gave us examples of how the medieval to kind of like Middle Ages and even Renaissance level Arabic mathematicians were primarily focused on using the zero to keep the numbers in the correct place. So I'll just comment here. Zero as an arbitrary midpoint for measurement purposes within a single quantity is similarly trivial, whether it be time, for example, BCE and CE, the old AD and BC, or above and below a surveyor's foundation line as used for construction in ancient Egypt. That sort of zero is really an index point for purposes, and very often we might decide to change that 0 point, and it doesn't make any difference to the quantities, the nature of the quantities involved. So thus, I conclude the oldest original extant definition of zero, compatible with laws of physics describing our universe, originated with Brahmagupta in India, 628 CE. And many people have mentioned Brahmagupta, and I'll just remind viewers that he was an astronomer and not an accountant, so we shouldn't interpret Dana and Rina as fortunes and debts and so on in financial terms. He was really dealing with negative and positive magnitudes. So I've had a slightly more impressive and uplifting illustration of Brahmagupta created as an astronomer compared to the traditional image for Brahmagupta, which is the sad, downtrodden looking black and white image doing diagrams on the ground. So what I've done is I've gone into the Sanskrit of Brahmagupta's shlokas, his verses that describe his sutras or his laws of integer arithmetic. And what I've done, just for the sake of visual convenience, is the black words are positive, the red words are negative, and you can see the references to zero, which are neither positive nor negative, in the green. And you can see that the Addition Sutra number 4 is the most important concept, I believe, in the launching of zero as a number in its own right for the purpose of scientists. And this definition appeared in his chapter 18 of Brahmaspita Siddhanta, which was a chapter on algebra. And if we continue on, we can see that there are also the Subtraction Sutras, and we can see that one of the most contentious differences between Brahmagupta is Subtraction Sutra number 3. If a larger negative or positive is to be subtracted from a smaller negative or positive, the sign of the difference is reversed, negative becomes positive and positive negative. So that simply means that if a larger number is subtracted from a smaller, the sign changes. So if we've got -7 minus -4, the answer is -3. Now, the sign hasn't changed, and so therefore -4 is less than -7, which is not how we interpret integer ordering today. So here we again see the multiplication sutras with the Sanskrit at the top, and we can see that again and again, Brahmagupta mentions 0 very deliberately again and again. So in the addition sutras, we can see he doesn't just say that when you add 0, it has no effect. He says, you know, positive plus 0, negative plus 0, and 0 plus 0. So he is really hammering home the importance of India's 0 for the purposes of Indian algebra. So there are the multiplication sutras, and the one which is giving problems to children today, the product of 2 negatives is positive. That becomes something that is very easily understood if you understand the definition of 0. So if you accept that 0 is defined as a sum of equal and opposite quantities, we could say that 1 plus 1 is 2, or what we can say that this one here is -1 and this is +1, and together they sum to 0. Now, -1 multiplied by -1 actually means -1 subtracted from 0 one time. So if we take away the -1 from 0, we see that +1 remains. And that's a very simple instantiation of -1 multiplied by -1 equals +1. Child's play, in fact, but we don't have such simple ideas because the algorithms that we use today are actually incorrect, because the transmission of 0 as defined by Brahmagupta never made it to classrooms in 2022. So there's the 4 division sutras, just to kind of round them off with the Sanskrit again at the top. So I talk about the symmetry of India's concept of number, and here I've got a diagram where we have, on one side we have black squares and we have black numbers, and on the other side we have grey squares and grey numbers. So if we think about 0, we can see that 0 represents the least number of either type of quantity. And it's very obvious from this symmetric diagram that 5 grey squares are greater than 2 grey squares. And similarly, 5 black squares are greater than 2 black squares. So we've got a lovely concept of symmetry here, where 0 is the least possible number. Now, if we just consider that mathematics is meant to be the language that the universe was written in, well, the universe is comprised of matter and energy, and the least quantity of matter and energy that you can ever have is 0. So if numbers represent counts or measures of quantities, you cannot have a negative number representing a count or a measure of a quantity that's less than nothing. So we started off with a concept of 0 from Brahmagupta, which is incredibly simple and intuitive and common sense. If we were to travel from 0 3 kilometers west, that would be the same magnitude if we traveled from 0 3 kilometers east. So if we think about maps and distances and so on, a natural number line would always have equal and opposite magnitudes in opposite directions. And we can see here from this, when the number of positive and negative quantities are equal, the sum is 0. Now, I quite deliberately haven't labeled either of these sides positive or negative, because that sort of decision, when we think about the universe, is completely arbitrary. The mathematics of 0, positive, and negative will work perfectly regardless of what we say defaults to positive. And as a bit of an amusing thought, we have positive numbers off on the right-hand side of our number line, and we've got the negatives off on the left. And that concept came from England in the 17th century. And that's because perhaps they were fighting the Dutch at the time, and they were wanting to advance in an easterly position, and that was positive for the military. Now, if the British had been fighting the Irish at the time, it's quite possible that the orientation of our number line with 0 in the middle might have had positive numbers on the left and negative numbers on the right. So that's not what came to our classrooms at the moment. I'll show you the current concept that we have based on our lost logic of 0 later on in this presentation. Now, here, just look at with your eyes. The East, as their sort of approach to mathematics, is often said to be more practical and empirical than the West, which is more abstract and theoretical. And perhaps the Middle East is a little bit in between in that regard. But here, just look at these ideograms at the top left. We've got 1 positive is definitely less in count and multitude and magnitude than 3 positives. And similarly, reading across the top row, 1 negative is a lesser quantity than 3 negatives. And moving across, 2 negatives is the same as 2 negatives. And we see then we have an equality sign naturally emerge out of that, like an equal sign. And then we've got, moving across, we have 3 negatives, a greater quantity than 1 positive. And we know this to be true because if you sum 3 negatives and 1 positive, you'll end up with 2 negatives as the sum. So, and if we look at the second row, we can see 1 negative is less in quantity than 3 positives, and so on. Now, this is the correct concept of integer ordering that should have emerged had the empirical style of mathematics from the East actually migrated to Europe by the time that the Renaissance kicked around, but it just didn't happen. So I've created a new mathematical symbol, which is an equal sign inside a circle, which is a symbol to represent equal and opposite. And you can see at the bottom right-hand side, I've written 2 positives are equal and opposite to 2 negatives. Why? If you sum them together, they sum to 0. And that's how 0 is meant to be as symmetric as the circle that describes it, because 0 is actually possessing a dual identity of equal numbers of 2 different types of quantity, negative and positive. So there might be a little bit of overlap between what I've been talking about for the last few years and what Jeff just shared. But here we've got Al-Khwarizmi, who says, I'd seen that the Indians had set up 9 symbols in their universal system of numbering. And so they made 9 symbols, which are these: 9, 8, 7, 6, 5, 4, 3, 2, 1. And every number is put together above 1. So Al-Khwarizmi doesn't mention 0 in this introduction. And he then goes on to say 1 is the root of all number and is outside number. So he didn't mention 0, and he doesn't consider 1 to be a number. And I'm just going to focus on the red bolded text for convenience. So Al-Yuklidisi, forgive the pronunciation, he considered 0 a placeholder, but not a number. And he talks really about why are the Hindi letters 9? So much for the 9 letters. 0, the aim is only to occupy the place. This is what Jeff mentioned before. We multiply the letter by 0 to occupy the place and tell that there is a place and that it's empty. So Al-Yuklidisi, some 300, more than 300 years after Brahmagupta, is mentioning 0 as a placeholder, but only in the fact that 0 reveals an emptiness, and it is not to be considered a number. So 200 years after Brahmagupta, Al-Khwarizmi didn't accept 1 as a number, and so we can obviously then conclude that 0 as a number was never something that Al-Khwarizmi would have considered. And 300 years after Brahmagupta, Al-Yuklidisi accepted India's 0 as a placeholder, yet not a number. Why? And that's because Al-Yuklidisi means the Euclidist, and he was known for his skill in studying the Greek geometry of Euclid and translating it into Arabic. And in Greek geometry, there was no concept of negative magnitude. And if I just digress for a moment, there could very easily have been a concept of negative magnitudes arise out of ancient Egypt, because it is said that geometry arose out of the annual flooding of the Nile. And so for the purposes of taxation, they had to measure land to compensate for the amount of lost land as a result of the Nile flooding and taking away farmland. Now, just consider for a moment that there were 2 different types of people working the agriculture. What if there were fishermen casting their nets on the Nile? They would consider the flooding of the Nile to be a positive event, and the more surface area that they could toss their nets, the more positive it would be for them, and it would be negative for the farmers. Similarly, when the Nile subsides, that would be positive for the farmers, but negative for the fishing people. So it's quite possible that there could have been a geometry of positive and negative magnitudes, and yet that for some reason just didn't arise. Maybe there was no taxation done on fishing with nets at the time. So as mentioned before by Jeff, around 300 BCE, Euclid defined number as a multitude of units. So Euclid's definition of number came before 0 and 1 were numbers. And that means that India, while it defined 0 as the sum of opposing negative and positive numbers or quantities with the same multitude or magnitude, now, we all had told that the Indian mathematics was picked up and enhanced by the Arabic writers. But if the Arabic and European writers in medieval times really understood India's 0, where are all the negative numbers in their writings? There aren't any. Now, what has actually happened, it's very interesting, is because people assumed that 0 is a placeholder, but positive and negative would have traveled into the Middle East and into Europe. People then started to falsely equate the subtraction of positive numbers in Arabic algebra with the presence of negative terms. And so many people say that the method of Al-Khwarizmi was to eliminate the negative terms. No, there were no negative terms in Arabic algebra, just positive terms being subtracted. So algebra, the word, has often been kind of like associated with negative quantities, because algebra was all about supposedly removing negative quantities and then confronting positive terms on either side of an equilibrium. But that was not what happened at all. So here's a fun diagram where we can look at the a very truncated and summarized history of the travel from east to west. And if we look at on the far right, in Binmal, India, we can see Brahmagupta, and I've got the old sad Brahmagupta. I should update this with the happy, powerful looking chap. But the transmission of 0 as a placeholder was done, but what traveled from India west was not as defined by Brahmagupta. So as it went west into Iraq, we saw that the 0 as a sum of equal and opposite positive and negative quantities was not something that the likes of Al-Khwarizmi, Al-Uqlidisi and others ever contemplated at all. And it was incredibly rare if any Arabic writer wrote about a solution to an algebraic problem that had a det or a negative term. Very, very rare occurrence. And as Jeff mentioned before, the Arabic world really focused on positive numbers only. So then from the Middle East to the tip of North Africa, we've got Leonardo Pisano, also known as Fibonacci, who introduced supposedly the Arabic numeral system based on the works of India. So Fibonacci studied this well, as his father was a trader in North Africa, and then he brought the mathematics of the Arabs, and supposedly based on the works of India, to Italy, and from Italy then it eventually arrived in London, where the most influential writer who shaped the world's view of 0 was Robert Recorde. So in this box here, we see those unaware that 0 was defined as the sum of equal positive and negative, included Al-Khwarizmi, the traders in North Africa, Leonardo Pisano, and Robert Recorde. And Robert Recorde's book, The Ground of Arts, was published for around about 150 years. It was the standard introduction to decimal place value arithmetic in England. And just for a comic relief, I've got the voice bubble. I invented the sign equals and introduced the pre-existing sign plus to England. Yet I never knew about your 0 definition, Mr. Brahmagupta, or laws of positives and negatives. Now, what I've got in the fine print here is Robert Recorde did know that a subtraction subtracted is addition, yet this is an adjustment done on positive terms. There are no negative terms. And people have been conflating the subtraction of positive terms with the presence of negative terms, going all the way back to the writings of Diophantus in Arithmetica. It's there have been lots of anachronistic errors in the interpretation of the evolution of mathematics. So here we've got a page from 1685 out of John Wallis's Treatise of Algebra. And if I just summarize the diagram that appeared in 1685, John Wallis had this very simple line. And in his book, he said that a movement from an origin, which is A, to D, was less than no movement at all. So John Wallis said that a movement from A to D was in effect an advance that was less than nothing. So this is the original concept that led to the idea that if we just say that A, replace A with a 0, any magnitude to the left of 0, by arbitrary whim of John Wallace, who used a military metaphor, is said to be less than 0 or less than the origin point. And the reason is it was a military metaphor, and advancing east was the objective. And if you moved west, you must have been retreating, and that was negative as regard the generals. Now, I'll just say that there's a wonderful symmetry in life as well as mathematics, and that is that all of the mothers, wives, and girlfriends and daughters of all of these soldiers would have had a completely opposing opinion. They would have said that moving west towards home and safety would have been positive, and advancing towards the enemy would have been negative, because you would have been closer to injury and possible, or even maybe likely, death. So we can see that we started off with this lovely common sense idea of 0 being a lovely position of balance, which is natural, that 3 left is exactly the same as 3 right, but in an opposite direction. And yet from John Wallace, who didn't have in front of him all of the writings from the Sanskrit from ancient India, he just kind of like was stuck in this Euclidean mode where only positive magnitudes were to be considered, and anything that was subtracted in excess must have been less than nothing, as opposed to something of an opposite kind. So I just wanted to also mention at this point and highlight there's 2 types of mathematics that came out of ancient Greece that people are not really that aware of today. We've got arithmos and we've got arithmoi, and you can see there in the finer print we've kind of got applied mathematics is considered to be Eastern and practical, and we've kind of got the cliche that pure Western mathematics is all about number theory. So arithmos, as Jeff was talking about before, is always numbers associated with noun objects. So in arithmos, the numbers represent usually adjectives describing quantities of objects, like 5 horses. 5 is an adjective, horses is the noun. Whereas in arithmoi, there are no objects other than the abstract units which comprise the number. And unfortunately, all of the children up to probably around about year 10 or year 11, they want practical solutions to real world problems that involve arithmos. And that means that we want to learn symmetric, science-friendly types of definitions of 0, where negative and positive are equal and opposite, because that's exactly how things like Newton's third law works in reality. Newton's third law, every action has an equal and opposite reaction. Well, that's perfectly consistent with the writings of Brahmagupta. Whereas arithmoi was based on the philosophy of ancient Greece. And interestingly, the philosophers of ancient Greece usually had slaves, and the real mathematics was always done by the tradies and the working class, whilst the philosophers really led the debate about where mathematics went in the future. And even today, I think it's a little funny that we study science, we might study applied mathematics, but we're still called a doctor of philosophy as opposed to a doctor of science. So in China, as well as India, China and India, they were more practical in their mathematics. They were interested in astronomy, navigation. Navigation, very, very important for trade and pursuing wealth. And also astronomy is very, very important for agriculture, for predicting when the crops should be planted, when the monsoons are going to come, and so on. And China and India had a real focus on symmetry, where negative and positive were equal and opposite. and that formed a concept of a nothing in China, as I'll show you shortly, and also a zero in India. So I showed you before what I call the basic lines, or the B lines of Brahmagupta, because we've got two lines on the x-axis. We've got one going towards the west or the east, depending on which way you're looking at this diagram, and an opposite line going in the opposite directions. So both of these lines have arrowheads on them, meaning that the least quantity, the least magnitude is zero, and there are two infinite directions of infinite magnitudes on either side. So zero is also the sum of the real number line. Now, we can also see a similar sort of approach to the ancient Chinese, and I've got the L lines here of Lui Hui, not the right pronunciation. I haven't heard that read out before. And it's got here, I'll quote, "I read the 9 chapters on the mathematical art, circa 100 CE, as a boy, and studied it in full detail when I was older. I observed the division between the dual natures of yin and yang, the negative and positive aspects, which sum up the fundamentals of mathematics." Now, this diagram here is kind of an interpretation of the Chinese rod numeral arithmetic. And in China's rod numeral arithmetic, if you had one red rod, that would have been considered positive, and if you had one black rod, that would have been negative. And if they occurred together, they would cancel each other out, and they would be removed from the calculating table. So nothing in this sort of interpretation was the least quantity or the least number out of the Chinese culture, but they did have a natural symmetry, and as it's written here, it was consistent with the philosophy of yin and yang. So apart from the fact that the Chinese had a kind of a concept for nothing, but they never really had a symbol for a zero until I believe around about 1247 CE, when it finally appeared in China's mathematics texts. So what we see is that Europe, especially from the Renaissance, was captured by the geometry of Euclid and the number theory of Nicomachus of Gerasa, and before that Pythagoras. And number theory was often associated with lots of abstractions, and 1 and 2 weren't numbers, and there developed an asymmetry where negative was considered to be less than positive. And yet we know that if you've got one negative electron and one positive positron, they sum together, they cancel each other out, release a photon, and one electron and one positron sum to a zero, or perhaps a nothing, as the universe might consider it. So here, getting closer to the end, I have the W lines of John Wallis, and this is based on his initial diagram from 1685. And if we just consider the A point in the middle there to be a zero, he only defaulted with number being one direction only, and that was in a westerly direction because that's where the military wanted to march, and any magnitude which to the left of zero, or the origin, or the A in this diagram, would have been a bad day's marching because you've retreated. So it was a pejorative negative. It was a pejorative less than nothing from a military perspective. And so this concept of negative magnitudes being less than zero, as I mentioned before, is impossible in the laws of physics. And principles of structural engineering based on physics always require Newton's laws to apply, where every action has an equal or opposite reaction and forces always come in pairs. All of that is Eastern mathematics applied to science. You don't ever see in science people saying negative magnitudes or quantities of negatives being less than 0. No, they just have opposite attributes to positive quantities. So you can read the fine print at leisure. So what I noticed as a child and through my schooling was that 0 was not understood today. We don't have a grasp on the correct interpretation of how 0 should be used in mathematics education. And there are a whole lot of problems, paradoxes, and inconsistencies that arise because India's 0, which they created by the 7th century, it was probably around for at least a century before that. Perhaps Brahmagupta might have been a bit like a Euclid and summarized a lot of Indian mathematics that was around at the time. But as a student, I was noticing things like the product of two smaller numbers or two smaller factors can be greater than the product of two larger factors. Now, that sort of thing just does your head in, because you have -3 multiplied by -4 equals +12, and yet the product of two larger factors on the number line, like +1 multiplied by +2, is less. The mathematics is absurd because it's all based on philosophy and axioms that we only value what's on the right-hand side of 0. And that's a positive sort of a vibe, and anything to the left of it is negative. Just consider the word, as opposed to equal and opposite, as it is in the real world. So here's another example of inconsistent arithmetic today, because the 0 vanished as defined by India and Brahmagupta. So consider fractions. They are equal if they both have the smaller number as the numerator and the larger number as the denominator, or vice versa. So we can see that +2 divided by +4 equals +3 divided by +6, but +2 divided by +4 doesn't equal +6 divided by +3. That's all fine. There's another example there as well, where we have larger numbers divided by lesser numbers on the left, and we mix up the ordering of larger and lesser, and it doesn't work. Now, we know that +1 divided by +2 equals -1 divided by -2. So therefore, -1 has to be less than -2. We know that one negative is less than two negatives. We saw that with our eyes before, with those differently styled inequality symbols. And we see here that for those two fractions to be the same value, mean the same number, they both must have the smaller number on the top as the numerator and the larger number as the denominator. That's very simple to understand, but that's not what is taught around the world today, because India's 0 vanished. It seemed to disappear as if it was a fleeting mirage. So that's pretty much what I wanted to share with you in this talk. My paper will go into a lot of textual detail and go into a lot more detail on algebra and so on. But I wanted to give a little bit more of a visual vibe that really explains why people really struggle with the foundations of mathematics today. Mathematics around the world is almost universally the most disliked subject, and it doesn't pay to think too hard about how the foundations of mathematics works, because you will very quickly experience cognitive dissonance. We know that 5 negatives are greater than 2 negatives. We are told by law And it's a rule, we've got to obey the laws and the rules, that somehow -2 or 2 negatives are greater than 5 negatives or -5. It's just crazy stuff. So that's the whole reason why I set out to explore zero. I began in 1983, and really it's been an amazing adventure looking at all sorts of different cultures. But my viewpoint has always been to focus on the very simple foundations of mathematics and how they seem to have become lost, and mathematics has gone backwards in its clarity compared to the simple writings out of ancient India. Now, I'll just make one final comment on whether or not China, their nothing, would be considered a number. And it's a little similar to the Arabic experience, and that is that when there was subtraction to be done in ancient China, and they would have an empty space in the minuend, and they would have a number underneath it as the subtrahend. The explanation was, in the rod numeral arithmetic, is that when there was no number facing the subtrahend, you simply reverse the colors of the rods in that place. So that to me indicates that the practitioners of the rod numeral arithmetic, like the Arabic world, was really just saying when there's not a number there, this is what you do. So the not a number there in the vacant columns of China's rod numeral arithmetic really, like the Arabic experience, indicated there was not a number there. So it seems to be a little contradictory to think that not being a number there is somehow to be interpreted as being a number that is not there. So I'll finish off there, and I just want to say I'm greatly honoured to be included amongst the very high calibre of speakers involved with this project, and I'm very happy to be challenged or take any questions from the panel.
Right. Well, thank you, Jonathan. We'll get to that in a minute. A couple of comments from myself to abuse my position is that reference back by you to Brahmagupta, as you've indicated, most people do trace the modern zero to Brahmagupta's work. It's the one that we inherited and that we embellished. But the question for the Zero Project is slightly different. We take that as starting point, but the question is, where did Brahmagupta get it? And as you suggested, and others have, that he was a systematizer and systematized the mathematical knowledge that was available in his time. The question is, how did it reach him, and when did it reach him, and how long had it been around, and in which?
Okay. I'll give you another input into this, and that is that from the Surya Siddhanta, the Sun treatise, which is a much older treatise on astronomy than even Aryabhata's writing, it was well known that if north be considered positive, that south would be negative. So if you had angles of inclination from the equator north as being positive, and if you had angles from the equator south being negative, then if you had no angle on the equator, perhaps if it was midday or something like that, that would be a midpoint, that would be a sort of a zero angle. Now, the dating of the Surya Siddhanta and its sort of opposition of north and south being positive and negative is very unclear. It was definitely around by 800 CE, but many people also say that different versions of that treatise were around, possibly another 800 years before that. I think
Okay,
that the reason...
Jonathan, if I may,
Yeah.
we don't want to delve into too much detail. We still have the panelists. I just wanted to enter two comments. One is that we do want to go back. Surya Siddhanta and others, we're pursuing all those leads. But the question is, did India invent, if indeed there is a distinction between the placeholder 0 and the numeral 0, was there a moment in Indian history when someone from that, say, the subcontinent, invented something that we refer now to as the number 0 as distinct from the placeholder 0? That's the question.
Okay. Well,
please, no further comment. You get another chance in a minute.
Yeah.
When I get to the panelists. But the other issue being that if it is a modern concept, then we're on a wild goose chase. If there was no clear distinction between a placeholder 0 and number 0, then we're chasing something that is just a myth. The other thing is that if it is indeed something modern, then we should look at it from a completely different perspective, and that would be one of modern mathematics and semiotics, in which you still speak about quantities and directions and all these things, but in modern mathematics, the numbers are totally divorced from any empirical data, and they're just simply numbers to be manipulated and to be part of a system and to be coherent within that system. And so totally different considerations would apply there as to positive, negative, and all that, as long as they're consistent with the abstract concepts that define that modern mathematics. And so that's a totally different issue, and we may be conflating those two and giving ourselves a lot of work that may prove to be very interesting and instructive, but not particularly pertinent to the Zero Project. Was there a numeral 0, and was it invented? So let's leave it there for now. I just want to go back to Jeff and ask Jeff if you have any questions for Jonathan, and then Jonathan, if you have any questions for Jeff, and then we'll finally get to the panelists if they're still patient and with us. Jeff, any questions for Jonathan?
I don't think I have any particular questions. I just want to point out one thing about Al-Khwarizmi and a little remark about 1 not being a number. That was interpolated in the text by a later editor. But it is common, well, not terribly common, but it does occur in medieval Arabic texts that they would take some Euclidean idea, like that 1 is not a number, that numbers begin with 2, and insert them in the beginning of an arithmetic text. And then the author would ignore that and work with fractions and regard 1 as a number anyway. Certainly, Al-Khwarizmi regarded 1 as a number. There's absolutely no question about that. That was just, you can tell it's an interpolation because at the end of that passage, he says, and now back to the book.
Right.
These are the words of a copyist inserting his own remark into a text. Al-Khwarizmi himself would not have written, and now back to the book.
Right.
So I just want to make that just one minor clarification.
Right. Got the point. And I think it comes down again to what I was saying, but then in a different sense. We're talking about two things, semantics and syntax. It seems that they had the syntax down. They knew what to do when there was an empty place or 0. Right. But they spoke about it in different terms, and that's what's confusing the issue here. But I think we're getting clarity on that as we move along. Jonathan, any questions for Jeff?
I really enjoyed your presentation, and I also just want to point out that the reason we add up numbers is based on your instantiation of addition from the Arabic approach, where the sums appear at the top of columns of numbers, whereas the modern approach is that we add down and write the sums at the bottom, but that's why we get the expression add up numbers.
Oh, I didn't know that. Yeah, thanks. That's interesting.
Thank you. Okay, finally, Jim, you've been very patient. You've heard the two speakers. And from your particular perspective, from Mesopotamian mathematics, whether you can see any cross-references there, please introduce yourself briefly in your own words and then fire away with your questions, please.
Okay, my name is Jim Ritter, and I am a historian of mathematics. and particularly with a particular interest in ancient Mesopotamia as well as modern history of relativity theory. I have a question to Jeff first, because I was struck by the parallels between what you said, Jeff, and what I will be saying in a few weeks' time about Mesopotamia, that there are these two traditions, much even more distinctive in the Mesopotamian case, different one from the other. But I would just like to ask you about a thing that concerns me, which is the nature of what Peter was just talking about, that is the distinction between the semantics and the syntax, if you like, or between the sort of the names that are used to apply and the rules that are used to operate on. And I would like to just have a feeling about to what extent is something that you mentioned at the end, Jeff, to what extent does the process of operating on numbers and zero invoke or inflect a kind of substantiation of zero as belonging to the same class of concepts as the other numbers.
Yeah, that's something I've paid a little bit of attention to, because I noticed that in Renaissance mathematics, they really did start treating zero more formally, and they introduced, of course, negative numbers and complex numbers as well in kind of a formal sense. The one thing that grounded the medieval Arabic arithmeticians is the fact that everything had to be spoken. So there was no notation that existed apart from speech. And if you speak it, it has to make sense. So this is why every author will say that the zero signifies an empty place where there is no number explicitly. They say this, and then they'll work on it. Now, okay, there's a huge backstory to this that I actually don't have time to get into. It has to do with my investigations in the medieval Arabic and Renaissance algebra, where I've noticed that the introduction of notation independent of speech in 16th century texts really is the first step towards regarding these objects as in a more formal way, where syntax takes precedence over semantics. That happens in a number of instances in the 16th century in European texts. And I kind of lumped zero in there, although it's very difficult to understand how it is people were thinking about these when they were working on them. I don't know if I answered your question at all.
You certainly are on the way to doing so that's fine.
Yes.
That's fine. Very good. I don't know what the time situation is like.
This is a special session, so I would say, even though we're running long, let everyone have their say.
Okay, well then let me just ask a question of Jonathan.
Yes.
I was struck by in the early part of your talk, you were talking about what you seemed to imply was a universal way of introducing multiplication in elementary mathematics, and the examples that you gave, however, were all from English-speaking countries. What has struck me is the emphasis on Euclid and the manner in which one introduces elementary concepts at elementary levels differs greatly over history from one country and one culture to another. This Euclid-centered idea of elementary education, elementary mathematical education, is not and was not as strong or even particularly present in a number of other cultures. I'm thinking of France, for example, 18th century France. This is not at all the way in which elementary arithmetic was taught and in which multiplication was introduced. So my question to you is, have you looked at other cultures other than the English language one in terms of differences in major differences in elementary mathematical education?
Yes, I have. And I'll just point out that the problems that emerged in the English language were due to an incorrect translation of Euclid in 1570. But prior to that, Tartaglia had translated the elements correctly in 1543, and Schobel had translated it correctly in 1555, and the French Forcadell had translated it correctly, I think, in 1565. So when the Americans, after the Civil War, were looking for mathematics texts for their universities, they'd turned to translating French mathematics textbooks rather than English ones. And Professor John Farrer, who wrote some of the introductory arithmetic books for the universities, specifically said that the French mathematics was explained far better than the English. So we can see that it wasn't just the bad blood because of the American Civil War. They were actually translating from French because it was more clearly explained and it was less Euclidean in nature. So does that give you part of your answer?
I mean, I was aware of this, but it does indicate to me that perhaps a larger view would be a little bit less critical in universalist terms than perhaps the impression one might get. Okay, fine. That's fine for me.
Okay, Jim, we look forward to your talk also because of the novelties that you'll hopefully be introducing at that time. Friedhelm, you've also been very, very patient. This is your chance. Go for it.
Yeah, thank you. Yeah, I'm Friedhelm Hoffmann. I'm professor of Egyptology. I'm mainly interested in late stories written in Egyptian language, but I happened to come across some notations of, let's call zero, but it's in fact the absence of numbers. So I will demonstrate this in my lecture in some weeks, and I have to say, in the same way as Jim did, this picture I'm going to draw will very much correspond to what Jeff showed us today. I would like to ask you, Jeff, a question. You mentioned that numbers in the Arabic mathematical world were always taken to be numbers of something. So and so many horses, for example, but not 5 as an abstract concept. Didn't they have any multiplication tables, for example, in their handbooks? Or what about the example you showed to us with the square roots of numbers?
Mm-hmm. Well, yes, they did have multiplication tables, especially in base 60, of course. But those are the quantities for which there are understood to be units attached. So they're just not specifying the units. In fact, if you read Arabic arithmetic books, they generally do not mention the units at all. But in some books they do, because, in fact, I wrote a longer version of the paper in which I gave quotations from Ibn al-Bana and another mathematician, Ibn al-Hayy, where Ibn al-Hayy states there are two kinds of division: the division of a type by the same type and the division of a type by another type. So there are other authors who mention this too. But he also says that when you actually do the calculations, the answers are the same for either one. So there's no point in actually mentioning it. So most textbooks will only give you the rules for doing the operations. It is assumed you have units attached to them.
I see.
And what makes these books universal is units can be anything you want them to be. That the operations are still the same.
Okay, thank you. This makes things very clear. And also to you, Jonathan, I would like to ask a question, or to all of you. Brahmagupta, is it historically attested that he, let's say, wrote his book in 628? Or are the texts under his name ascribed to him later?
That's actually dated in the text,
okay,
because it was associated with the Indian calendar system, which translated into the year 628. And there are lots of other commentators who started providing commentaries on the Brahmaspita Siddhanta shortly after that. And the dates of their writing is similarly known as well. A lot of Indian mathematicians would say, I'm the son of so-and-so who lived at this time and so on. So it is well accepted and clearly dated as 628 CE, yes.
Okay.
Any other questions, Pritham?
No.
Okay. Well, we look forward to your talk as well, because all of these are supplementary. They will fit together and give us a better overview, because this is really what's been lacking and why we launched the Zero Project. We have single authors giving their perspective and, ending up basically speculating and leaving it at that. And no one's suggesting that, why don't we just do this research and put all this together. Mayank, you've been also very patient and had a narrow escape. I don't know if, anyway, we won't get into the personal aspect of it. But please, you've listened to all of this. I know you were invited because you always have had a very distinct interest, but also a distinct view about what the difference might be, if any, between the placeholder and the number and what it might take place. Please, if you would just briefly introduce yourself and then take it from there.
Yeah, so I'm Mayank Vaya. I'm from Mumbai. I used to be an astronomer actually till I got interested in zero and numbers and history of science and so on. And now my interest in zero has been seriously awakened by this participation in the Zero Project. And I had a comment to make about Jeff's presentation, which is very brilliantly done, which is that this idea of dissociating the association of a number with value, that any number essentially either explicitly or implicitly meant an entity behind it. Either there were is something that we do even in cognition for children. When we give children their first books of numbers, we give them 1 apple, 2 oranges, 3 whatever buffaloes, and then we expect children to make that quantum jump. And there are many who have associated that quantum jump with actually a creative jump in the brain's wiring because of the level of abstraction that it does. So there is something very fundamental about the abstraction level required before humans could make this jump of dissociating numbers from individual values to this idea of abstraction of numbers and their existence on their own.
Yeah.
And I think that is where this Peter's old contention that the environment, the philosophical environment of the culture adds to this help in shifting from this 1 apple, 2 oranges to 1, 2, 3, 4. So that I thought very interesting, that the idea even when they took the books from India to Arabia, they missed this point because this dissociation of number from entities is something was subtle and they didn't even realize. And I think Aryabhat and others themselves did not realize that they were making this important dissociation. It was a revolution that came stealthily, is my personal suspicion. As far as Jonathan is concerned, Jonathan, I think it was a brilliant presentation. Thank you for being awake till this late in the night. But this idea that bigger negative number is less than the smaller negative number is something that remains in Europe for a long time. So for example, when star catalogs are done, a star that is -5 in brightness is fainter than a star that is -2 in brightness. And my suspicion is that the concept is in the sense that if there is something is -5, you have to add 5 new entities to bring it back to 0. Well, if it is just -2, then you just add a little bit of -2 and then you get it back to 0. So the idea was that it's something that was deeper in the well and therefore needed to be pulled out with more effort, and therefore it was smaller this is my suspicion. I may be wrong on both these counts, but I still think they were interesting things to worry about.
Yeah, just to respond to that concept, that really arose as a result of how the West arrived at negative numbers via subtraction. So you've got to remember that when everything is a positive number in the West, you've got 5 minus 1 is 4, and 5 minus 2 is 3. The more you subtract, the less the sum. You get to 5 minus 5 is 0, and then the question became, well, what happens if you have 5 minus 6? It must be less even again. It's -1, and the pattern is that the difference has been getting less and less and less and less. No, what actually happens is at the 0 point, the opposite quantity starts to emerge, and the negatives start to increase. Okay, so it's a subtle thing. Once you get to 0, it's like it bounces onto the opposite unit, and then the quantity, magnitude, or multitude of that opposite unit then starts to increase.
Any follow-up?
Yes.
Mayank, any follow-up?
Yeah, just one statement. Yeah, that is true. What Jonathan said is true. But this idea that the star magnitudes of -5, -6 are fainter than the stars of -2, etc. This continuous line continues. That is the issue.
Yeah,
and
but
that's
what Jonathan is saying is that after the colonial period by the British, also the Indians were educated in that system, and so naturally you even yourself would have taken it over subconsciously, as it were.
Correct.
But that's another issue. We do not want to get into politics.
No, we do not want to.
Or environment. Okay, gentlemen. So I'd like to really thank you very much for this, and revert momentarily to. We will get to the other speakers in due course and do the same exercise, but we've always concluded with a survey, in this case for Jeff and for Jonathan. If you just briefly reply, okay, no more discussion, just briefly reply in a single sentence to the following 3 issues. One is, we've discussed it at length. Was the numeral 0 discovered or invented? Jeff.
Okay. I would just say it was invented.
Okay, thank you very much. Jonathan, was the numeral 0 discovered or invented?
Invented.
Okay. Jeff, was the transition between the placeholder and the numeral, which we've been discussing all this time, was it gradual evolutionary, or was it a disruptive moment in history?
It was a evolution via punctuated equilibrium.
Right. Jonathan, gradual evolution or disruptive moment?
I think gradual and transient transition. Not a big bang moment for sure.
Okay. Finally, and now we're getting to the working hypothesis of the Zero Project. If we're going to get anywhere with in-depth research, we need another working hypothesis. And so the idea arose that would it be mandatory to have the prior evolution of a sophisticated concept of nothingness or emptiness for the people at the time to even be able to conceive of 0 as a number. So the question is the concept of nothingness or emptiness that may underlie the invention of 0, is it trivial or profound? Jeff?
Well, it must be profound because I haven't figured it out yet.
And Jonathan?
I tend to have the view that it's trivial because it's empirical. If you've got a flock of 5 sheep and 5 foxes, you know that the foxes are going to consume the sheep. All assets have an opposite debt associated.
Jonathan, no discussion.
Okay.
And I think you really are a teacher at heart, and you avail of every opportunity to seriously edify the questioner, which is great. I really enjoyed it. But so thank you for joining today. We ran very long, but I've made an exception because it was such a special occasion that we have you 4 gentlemen together. So please, speaking now to the virtual audience, join us again the week after next to explore related issues to pinpoint, if possible, the Zero's epicenter. At that time, we will meet Irma den Hertog, a Dutch visual artist and art historian, on the immediate experience of being plunged into the great gaping void. So until then, thank you.